In recent years, China has made significant strides in revolutionizing aviation. They've built not one but two fifth-generation warplanes, the J-20 and J-31, and developed an arsenal of unstoppable hypersonic missiles. But now, the Dragon Country is ready to kick things up a notch. China has unveiled a new $13 billion aircraft that defies all laws of physics. Using hypersonic jet technology, this innovation aims to push the boundaries of global air travel, offering unprecedented speeds and capabilities that could drastically shorten travel times and reshape the way we think about flying. And of course, it will inevitably find specialized military applications. Beijing, John 3, Reuters. Chinese state media unveiled new images of China's most advanced aircraft carrier yet, including next-generation launch tracks that can catapult a wider range of aircraft from its deck. First shown to the public in June 2022, the Fujian was entirely designed and built domestically. Yet to conduct its first sea trials, the aircraft carrier is larger and technologically more advanced than the Shandong, commissioned in 2019, and the Liaoning, which China bought secondhand from Ukraine in 1998 and refitted domestically. On state television late on Tuesday, the Fujian was seen being towed by a smaller vessel with all of the three tracks of its electromagnetic catapult system visible on its deck. In the new year, we will seize every minute, work with determination, and strive for combat readiness as soon as possible, state television cited a Fujian officer as saying. The Fujian has been conducting tests, including mooring tests, before its sea trials, which some observers expected to have taken place by 2023. The carrier started launch tests for its electromagnetic catapult system in November, according to state-controlled Chinese newspaper Global Times. So, what has China done so far, and what remains to be done? Let's find out together. Hypersonic travel promises to transform the future of global aviation. This technology focuses on achieving speeds beyond Mach 5, 5 times the speed of sound. With this, a flight from New York to Beijing, which typically takes 14 hours, could be completed in under 2 hours. China has set its sights on this lofty goal with the Nanqiang No. 1. In 2023, this experimental jet reached Mach 6, a staggering 4,600 miles per hour. Designed by China's state-owned aerospace giants, materials of withstanding the extreme heat and pressures at such speeds. This accomplishment places China at the forefront of hypersonic technology, competing with the United States and Russia, who are also making progress in this field. China's ambition extends beyond air travel. They aim to dominate the next phase of the global aerospace industry, influencing everything from military defense to commercial space exploration. At these speeds, travel between distant cities becomes lightning fast. For instance, a flight from New York to London, typically 7 hours, could be completed in under an hour. China's commitment to dominating hypersonic technology is reflected in its ongoing investments and strategic alliances. The nation's ambitions go beyond enhancing air travel. They aim to secure a leadership role in the future of the aerospace industry, influencing everything from military defense to commercial space exploration. To achieve these extraordinary speeds, hypersonic aircraft rely on multi-stage propulsion systems. Traditional jet engines like turbofans work efficiently at lower speeds but can't handle hypersonic velocities. Instead, hypersonic aircraft use a combination of turbofan engines, ramjets, and rocket engines to optimize performance at different phases of flight. Turbofan engines are crucial for takeoff and subsonic flight. As the aircraft accelerates, ramjets take over, compressing incoming air and mixing it with fuel to generate thrust. At hypersonic speeds, rocket engines provide the final push to maintain speeds beyond Mach 5. Hypersonic flight, defined as speeds of Mach 5 and above, represents a new era in aviation. At Mach 6, aircraft can travel at around 4,600 miles per hour, enabling journeys between distant cities in a fraction of the current time. For instance, a 7-hour flight from New York to London could be completed in less than an hour. This dramatic reduction in travel time could transform long-haul flights, making it possible to cross continents or oceans in mere minutes. Turbofan engines are essential for the initial phases of flight, providing the thrust needed for takeoff. As the aircraft accelerates, ramjets take over. Ramjets, which compress incoming air before ignition, operate efficiently at supersonic and hypersonic speeds. Once hypersonic velocities are reached, rocket engines provide the additional thrust required to maintain speeds above Mach 5. One of the most innovative propulsion systems being developed is the multi-ducted twin turbine ejector ramjet, or the Mutter engine. This hybrid engine integrates turbofan, ramjet, and rocket technologies to address the challenges of achieving Mach 6 and beyond. The Mutter engine uses turbofans for takeoff, ramjets for high-speed flight, and rockets for hypersonic thrust. Maintaining airflow and combustion stability at these speeds is extremely difficult due to the pressures and temperatures involved. For example, NASA's X-43A scramjet reached Mach 9.6, but scramjets still face challenges with fuel mixing and heat management at such extreme speeds. Rocket engines are crucial for providing thrust at high altitudes where oxygen is scarce, allowing the aircraft to achieve and sustain hypersonic speeds. This combination of engines is essential for breaking the hypersonic barrier. However, hypersonic travel isn't without challenges. One of the biggest hurdles is heat management. At Mach 6 and beyond, friction with the atmosphere generates temperatures exceeding 2,000 degrees Celsius, hot enough to melt conventional materials. This heat can warp or damage the aircraft. To combat this, advanced materials like carbon-carbon composites and ceramic matrix composites are being developed. These materials are heat-resistant and can withstand the extreme temperatures of hypersonic flight. The Mutter engine also incorporates active cooling techniques, like liquid cooling and heat-resistant coatings, to prevent engine components from overheating. Engineers are adapting space re-entry technology to help maintain steady temperatures during high-speed flight. Testing of unmanned prototypes like the Nankiang No. 1 in 2023 has shown promising results, with speeds reaching Mach 5.8 and providing valuable data on propulsion and heat management. Despite its promise, hypersonic flight faces challenges like noise pollution from sonic booms. Breaking the sound barrier creates shockwaves that produce loud booms, disturbing populated areas. For example, the Concorde, which flew at Mach 2, faced restrictions due to its sonic boom. Hypersonic jets, flying at Mach 5 or higher, could produce even louder booms. Efforts to mitigate this include NASA's X-59 quiet supersonic transport designed to reduce sonic booms to a thump. However, implementing such technology in hypersonic jets remains a challenge, and strict regulations may limit where these aircraft can fly. China aims to achieve full operational status for its hypersonic aircraft by 2025. This could revolutionize commercial air travel, allowing passengers to travel from New York to London in under an hour. Business travelers in particular would benefit immensely from such rapid travel times. However, it's not all smooth flying.
Noise pollution, specifically from sonic booms, poses a significant challenge. When an aircraft breaks the sound barrier, it creates a loud sonic boom that can disturb people on the ground. The Concorde, a supersonic jet, faced restrictions due to its disruptive sonic boom. Hypersonic jets, traveling at speeds over Mach 5, could produce even louder booms. NASA is developing the X-59 quiet supersonic transport to reduce sonic booms to a soft thump. But applying this technology to hypersonic speeds remains a major challenge. Regulatory hurdles could also limit hypersonic flights over populated areas, restricting them to ocean routes. This could impact the commercial viability of hypersonic travel, as many profitable routes are overland. Despite these challenges, China is pushing forward with hypersonic technology, aiming to overcome obstacles like heat management, propulsion efficiency, and noise pollution. If successful, hypersonic travel could become a reality, transforming the way we fly and redefining global connectivity. The race to dominate hypersonic flight is on, and the future of aviation may just be faster than we ever imagined. However, predicting heat buildup and maintaining aerodynamic shifts during flight is still an ongoing challenge. Aerodynamic changes, such as those caused by altitude variations and flight speed fluctuations, can create localized areas of extreme heat which must be managed without compromising flight performance. Inconsistent heat distribution can result in unwanted stresses and potentially catastrophic thermal failures. Beyond the challenges of external heat buildup, internal heat generation poses a significant threat to the aircraft's electronics. At hypersonic speeds, the extreme temperature levels don't just impact the aircraft's structural integrity, they also affect the electronics and systems aboard the craft. Systems such as avionics, sensors, and communication devices are susceptible to heat-induced failures if not adequately protected. For example, during a hypersonic test flight, overheating in the navigation and communication systems could lead to a loss of control or critical data transmission errors. While technologies like heat-resistant semiconductors and liquid-cooled electronic enclosures are used in high-performance military aircraft, these solutions may not be enough to handle the extreme temperatures encountered during hypersonic flight. If cooling mechanisms are overwhelmed, the high thermal environment could result in system failure. Therefore, internal cooling for essential systems such as flight control computers, propulsion systems, and cockpit instruments must be robust and continuous. To tackle this, some researchers are exploring the potential of embedding micro heat pipes within the aircraft to transport heat away from sensitive components. These micro cooling systems, powered by capillary action, could help prevent electronics from overheating, ensuring the aircraft's critical functions remain operational. Nevertheless, even if we overcome this issue, there is still more work to be done. While the idea of traveling at Mach 5 or higher speeds is appealing, the design constraints necessary to achieve hypersonic velocities create numerous challenges for scaling these aircraft to accommodate more passengers. Currently, most hypersonic designs can carry only a handful of passengers, typically no more than 10. This limitation is due to the aerodynamic, structural, and thermal protection requirements. The design of hypersonic aircraft is focused on balancing extreme speed with efficiency, which restricts the number of passengers they can carry. One major reason for the low seating capacity is the need to reduce weight. Hypersonic flight requires extremely lightweight materials to minimize stress on the aircraft and enable high speeds. Advanced composites, such as ceramic matrix composites, CMCS, help reduce weight but also limit the available space for a passenger cabin. Every kilogram saved enhances speed and fuel efficiency, but this also restricts the number of seats. Additionally, the aerodynamics of hypersonic flight dictate that the aircraft must be streamlined to minimize drag and maximize speed. A larger, more spacious cabin would create unwanted drag and turbulence, diminishing efficiency and potentially compromising flight stability. Furthermore, hypersonic aircraft require advanced thermal protection to shield the structure from the intense heat generated by friction at speeds beyond Mach 5. The thermal shields that encase the aircraft's exterior take up considerable space, further limiting room for passengers. Scaling up these aircraft introduces significant thermal management challenges. As the aircraft's size increases, the heat generated by friction rises exponentially. A larger surface area leads to more heat buildup, and existing heat dissipation systems may be inadequate to handle the additional thermal load. This could necessitate even more sophisticated thermal protection systems, increasing the complexity and weight of the aircraft and making it less efficient. Structural integrity is another issue when scaling up hypersonic aircraft. The stresses experienced during hypersonic flight are immense, and larger aircraft would face greater strain on their fuselage, wings, and overall frame. While advanced materials like titanium alloys and ceramics help manage these forces, they are not perfect solutions for handling the combined heat and structural pressures at hypersonic speeds. These challenges hinder the commercial viability of larger hypersonic aircraft. More seats mean increased costs related to thermal protection, weight management, design, and construction. These complexities make it difficult to scale hypersonic travel beyond a niche market in the near future, resulting in limited seating capacity and posing significant economic challenges. Safety issues are also a concern. At hypersonic speeds, the challenges faced by pilots, crew, and the aircraft become exponentially more complex. At speeds exceeding 4,600 miles per hour, the kinetic energy involved is immense, and any malfunction or system failure could be catastrophic. The aircraft would cover vast distances in minutes, reducing the time available for pilots to respond to issues. Traditional emergency systems, such as parachutes, are ineffective due to the extreme forces at these speeds. Additionally, the aircraft's control surfaces may fail to operate correctly, making it essential to have highly reliable systems and fail-safes to prevent disasters. The friction-generated heat at such speeds can also damage the aircraft's structure, complicating emergency situations. New safety protocols and emergency response systems must be developed to address these challenges. Traditional aviation standards are inadequate for hypersonic flight, necessitating new guidelines for operations, emergency procedures, and certifications. Specialized systems are needed to manage unforeseen malfunctions, extreme weather, and emergency landings at hypersonic speeds. Rigorous testing is crucial, including simulations of malfunctions and tests of thermal protection systems. Developing new certification processes, pilot training programs, and safe landing protocols is essential to ensure hypersonic aircraft meet safety standards. These procedures are necessary to clear hypersonic aircraft for commercial use and ensure safety under extreme conditions. Even if hypersonic aircraft become a commercial reality, history offers a cautionary tale. The Concorde, a revolutionary supersonic passenger jet, achieved Mach 2 speeds, halving flight times and providing luxury travel. However, high operational costs, limited seating capacity, and environmental concerns, including the disruptive sonic boom, made it unsustainable for mass commercial use. Despite its technological innovations, the Concorde's economic inefficiency, fuel-heavy engines, and flight route restrictions confined it to a niche market. Its retirement in 2003 marked the end of an era, though its advances laid the groundwork for future developments. Looking ahead, China's Nankiang No. 1 aims to surpass the Concorde by achieving Mach 6 speeds over 4 times faster. These aircraft utilize advanced propulsion systems and materials to address fuel inefficiency and heat resistance challenges. The Nankiang's potential to reach low Earth orbit highlights a shift toward point-to-space travel, expanding the possibilities of air and space travel. With improvements in fuel efficiency, passenger jets towards limitations and make long-distance travel faster and more economical. However, the implications extend beyond commercial travel. Hypersonic technology could reshape military strategy, scientific research, and space exploration. Nations like China, Russia, and the United States are racing to develop hypersonic capabilities, influencing global power dynamics and security. Hypersonic weapons, capable of traveling at Mach 5 or higher, can maneuver at high speeds, evade defenses, and strike with precision. For example, China's Hypersonic Glide Vehicle, HGV, demonstrated a missile that circled the globe before striking its target. These weapons pose challenges for defense strategies worldwide. Hypersonic weapons, such as China's DF-17 missile system, could target military assets like aircraft carriers and radar systems, altering regional power dynamics, especially in conflicts like those involving Taiwan. The US and its allies face challenges countering these fast-moving threats. The development of hypersonic weapons reflects broader strategies to counter US aerospace superiority.